Before I do number 19, let me also mention that photons can have momentum as well, or also have momentum. Remember, momentum is our little p. At the end of chapter 37, we had this equation, the total amount of energy from special relativity squared is momentum times c squared plus mc squared squared. For photons that have zero mass, that's still true. Light doesn't have any mass. So this equation just becomes this. So we can move around this and say that the momentum of a light particle is its energy divided by c. Its energy is still hf, and so we end up with this. Its momentum is the h, again, Planck's constant divided by the wavelength. So let's do this problem. Number 19 has to do with the photoelectric effect. It says if the work function for a certain metal is 1.8 electron volts, the work function is this. It says what's the stopping potential? So that's Vs. What's the stopping voltage, stopping potential for electrons that are ejected from the metal when light of wavelength 400 nanometers is incident on the metal? So we do need to know the frequency. So we need to do c divided by the wavelength. For my own purposes, I learned a long time ago that I can write the speed of light in nanometers per second, and so I can divide this 3 times 10 to the 17 by 400 because they both have nanometers in it. So 3 to the 17 divided by 400 is 7.5 times 10 to the 14 hertz. So again, our relationship is that the light has energy initially, that becomes the work function and the kinetic energy, in this case the maximum kinetic energy, but the maximum kinetic energy is E, the charge on the electron, times the stopping potential, which is what I'm trying to find. And so the stopping potential is going to be HF minus the work function over E. Now I'm going to use my 4.136 times 10 to the negative 15 electron volt seconds as my H here, instead of the 34, the joules per second, joule seconds, because I want to just be able to use, I've already got this in electron volts, so I want to have everything in electron volts. So I multiply that by the frequency, 7.5 times 10 to the 14 hertz, subtract 1.8 electron volts, and we divide by E. So doing that multiplication, 15, I end up with 3.102 electron volts minus 1.8 electron volts, 1.302 electron volts over E. Now this is what I'm talking about with this E. Now this is the charge on the electron, and if the top was then written in joules, I would have to put in that 1.602 times 10 to the negative 19, the amount that E is. But here, because I have this E, it just cancels with that. And so my stopping potential is just 1.302 volts. That electron, basically just that E cancels with the E in the electron volts. The charge on the electron, that's what that E stands for in the electron volts, is the charge on the electron. We're just not writing it out because that becomes really small and weirdly small number in joules, but we can just leave it in this unit electron volt. And then when we divide by the charge on the electron, we just end up with volts. Technically, an electron volt is the amount of energy it takes to take one electron through 1 volt of potential, one potential difference. All right, so that's part A. What's the maximum speed of the ejected electrons? Now to do this, I am going to have to, sorry, my cat just jumped up here. I am going to have to probably get this in terms of the actual energy. So the kinetic energy, K max, is 1/2 V, and this is the mass on the electron squared. Now this is 1.302 electron volts, but dividing this by electron volts, the mass, it's easier for me to think of this mass, even though we have that weird mass with the electron volts per c squared, that really starts to be cumbersome. And so I am going to convert this to joules, where 1 electron volt is 1.602 times 10 to the negative 19 joules. So let me do that conversion. Okay, when I do that calculation, I move things around so that I end up with V, the speed, is just 2 times the total amount of the kinetic energy divided by the mass, and then take the square root. I get a speed of 6.77 times 10 to the 5 meters per second, which is very fast, but this is definitely still much, much less than 1/10 the speed of light, which would be 3 times 10 to the 7. Let's look at number 29 too. So number 29 says, what's the frequency, the photon energy, and the photon momentum in these very specific units of an X-ray photon having a wavelength of 35 picometers. So the wavelength, this 35 picometers, that's a pico is 10 to the negative 12 meters. 10 to the negative 12 is a pico. And so the frequency is c over that lambda. Here I'm going to go ahead and just write everything in terms of meters. So c over 35 times 10 to the negative 12 meters. So 3 to the 8 divided by 35 to the negative 12 is 8.57 times 10 to the 18 hertz. That's part A. The photon energy is h times f. Again, I'll probably use the Planck's constant in electron volt seconds. I could do it in joule seconds, but I'm going to do it with this. So multiply that frequency times 4.136 to the negative 15. Nope, I didn't multiply that. Times 8.57 to the 18th. I end up with 3.5445, I think, actually, times 10 to the 4. That's electron volts. That's a huge amount of energy for one particle to have. And then finally, the momentum, this is just the E divided by C. And so the fact that I already have this here, so this is 35.45 keV, right, 10 to the 4. So to 10 to the 3, that becomes 35.45. And so this becomes 35.45 keV over C. I already have it in keV, the energy, and so I can just do it this way. I could also have done h over lambda here to get that same momentum, but since I already had my energy in electron volts, it was easy enough to do it that way. Okay. Well, it's not too huge a jump to go from the statement saying, well, if light, which we were convinced is a wave, can act like a particle, could things that we've thought of as being particles, like electrons or protons, can they sometimes act like a wave? Can they do wave kinds of things? Can we get them to refract? Or can we get them to diffract? Can we get them to do interference? Things that particles don't do. Particles reflect. If they hit something, they'll reflect. Not always, but most of the time they'll reflect. Not necessarily with the same amount of energy. but you can get them to do that. But refracting and diffracting, interfering, this is not something that particles do. Particles do not have interference patterns. They don't do that type of thing. If you're going to sit there and try to get a particle to act like a wave, first you have to figure out what you're going to think the wavelength is going to be. And since this was the relationship between momentum and wavelength for waves, for light, deBroglie said, well, let's say that the wavelength is going to be of a particle would be h Planck's constant divided by its momentum. And so a particle would have a momentum if it was non-relativistic, which was just its mass times its velocity, or if it was relativistic, if it was moving very, very quickly, you'd have to do the relativistic momentum. And so then take these particles and try to do a two-slit experiment with them. So Davisson-Germer, the Davisson-Germer experiment is essentially electrons in a two-slit experiment, except it's more like the X-ray diffraction. It's more like the X-ray Bragg diffraction because you need to have really, really small distances. And so this is a simulation of the Davisson-Germer. So instead of having two slits, we're going to do this like we did with X-rays, where we have crystals that are where the atoms are evenly spaced in between here. And then we're going to send electrons. This is an electron gun, and we're going to send the electrons towards this. And we'd expect, if this was X-rays, we would get a diffraction pattern coming back on us here, where we'd have bright places and dark places. And in fact, this is exactly what is observed in an electron situation, where we actually get places which are brighter with lots of electrons there, and places where there's dark. And so these electrons are acting like waves. And there are places where we don't get any electrons, and there are places where we do get electrons. And if we change the speed, which would mean that we would be changing their momentum, we get a different pattern. As we change the speed, we have different amounts of momentum, and we get different patterns. You can actually make this look kind of like a face. And so the Davisson-Germer experiment says, yes, this absolutely does true. We do see a diffraction and interference pattern. And so these electrons do act like waves, where they have wavelengths which are based upon their momentums. Now, this is usually a pretty small effect, and again, you have to have really small spacings to notice it. Just to give you an idea of what kind of wavelengths these particles have, say I have an electron which is moving fairly quickly. Say it's moving at 25% the speed of light, so I would have to do a relativistic momentum. So if I do 0.25 c, I get a gamma of that, so 1 minus 0.25 squared. I get, a gamma of 1.033, and then the momentum should be that gamma times the mass on the electron times that speed. So times 9.11 times 10 to the 31 times 7.5 times 10 to the 7. And I get a momentum of this. Remember, momentum has very weird units. It's just a kilogram meter second. The deBroglie wavelength, I take h Planck's constant. If I have units of kilogram meters in seconds, I absolutely have to have units of joules seconds for my h, for all those things to cancel out correctly. Generally, we would have to have that for this, and divide that by the momentum I found from above, and I end up with this as the wavelength, 9.39 times 10 to the negative 12. So this is essentially 9.39 picometers. Or it's pretty close to 10 to the negative 11 meters. That's a very small wavelength, and it's particularly useful. In number 55, I made you this one in class, or I kind of do almost like it in here in this thing, but number 55, let's go look at that real quickly. From this chapter, talks about basically an electron microscope. So I don't know how many of y'all have ever really looked at an electron microscope or thought about it, but electron microscope essentially uses electrons as the wave that allows you to see this very small particle. So electron microscopes use electrons as the light, as the wave, to get details of the structure of something that's very, very small. In order to see something that's really, really small, if you want to see a detail which has 10 to the negative 11 meters as the size of the detail, you actually need to have light, or the wave that you're using to have a wavelength which is less than that. If it has a larger wavelength, it's not going to be able to distinguish those details. It'll essentially blur it out. So you need to have a wave with a wavelength less than that in order to see that types of that much. And so if instead of using an electron, you used actual light, actual photons, if you say, well, okay, I'm going to use light that has that type of wavelength, then the energy that each of those photons would have is some almost, millions of electron volts of energy. And if you actually hit your sample with something that has this much energy, you're likely to damage it or destroy it. And again, here's where I've got the H in terms of electron volts. But if you have an electron with that kind of wavelength, its energy is only going to be about this much. It's going to be much, much smaller, something like 5.26 10 to the 5 electron volts. So it's significantly less. Just a second here. Yeah, so this would be its total amount of energy. But the kinetic energy, which is this total amount of energy minus the rest energy, is only about 15,000 electron volts. And so when it hits that material, it's less likely to damage it than, say, the photon, which has got roughly about 10 times more energy. You can also have non-relativistic particles, non-relativistic momentums. So number 49 is similar to this one that I'm going to do right here. So in number 47, it says we have an old-fashioned television set, a CRT, cathode ray tube. This is also like the oscilloscope that we used in lab. So electrons are accelerated through a potential difference of, so it's a delta, that's a capital V electron, that's electric potential difference of 25,000 volts. And what's the deBroglie wavelength of these things? So remember that the kinetic energy that they're going to have afterwards is going to be the charge on the electron. So their charge times delta V. Charge on this is an electron. It's actually this. So is a negative electron times delta V. So E times this delta V. And then that has to equal 1/2 mv squared. This is the kinetic energy, their final speed squared times the mass times 1/2. And so we can get the momentum once we know that final speed. So we're going to use these top equations to determine the final speed, and then we'll use that to get the momentum, and then finally the wavelength is h over p. So let me go ahead and do this. We have 1.602 times 10 to the negative 19 coulombs times 25,000 volts. That's essentially this. That equals 1/2 9.11 times 10 to the negative 31 kilograms times V final squared. And so I can get V final. Okay, going through and doing this. So I have that the charge on an electron is 1.602 times 10 to the negative 19. The delta V is 25,000 volts. That needs to equal the kinetic energy, which is 1/2 the mass of the electron times its final speed squared. When I go through and do that, I get this. This problem specifically told us that relativity is not needed. This is about 1/3 or 30% the speed of light, so technically I would think relativity would be needed, but we'll go with them. The beta is about 1.03, sorry, the gamma, so I guess that's kind of why they're saying it. But anyways, so if we use that as our speed, again, times the mass of the electron, I get a momentum of 8.55 times 10 to the negative 23 kilogram meters seconds. And then using that in our equation for the wavelength, the deBroglie's wavelength, we get that the wavelength of this electron is 7.75 picometers. That's all I'm going to do in chapter 39. Chapter 38. We are going to do more matter waves in the next chapter, which would be on the next homework set and the next quiz. But this is all from this chapter in terms of matter waves. All right.